All right, thank you. I was also here 5 years ago, and haven't been back, in the last 5 years. But this year suddenly I have to be back again, because this work will appear also in ICML in about a month. So I'm Wotao Yin from Alibaba US Damo Academy, and in the US we are stationed in Bellevue near Seattle. We also have office in Northern California. And this is a work that I think is new, and it's a very powerful model that'll improve the performance, lots of machine learning. Let me just briefly look at the dominant paradigm in machine learning today, where you look for a model parameter, and I'll just call it a model, X, and such that the average performance of this model is minimized, where each term measures the loss of the model performing on a specific data point I. So it covers linear regression, SVM, and all the way to deep learning. And in optimization, this X can also mean, let's say, a step size or other kind of a solver configuration, and you optimize, you solve this model to improve the solver configuration on a set of examples represented at Fi. Okay. So, but what if I tell you that this small change will bring you or open the door to a much more powerful paradigm, where you, instead of looking for one model, you simultaneously looking for K models, and in terms of performance, every data point is assigned to the best model, and you simultaneously optimizing all these models such that the best performance for every data point is minimized. So while people I believe, have done this many times in the past, they have not formulated this problem explicitly. Perhaps because even if FIs are smooth and strongly convex, this whole model is non-smooth and non-convex. So it's not an easy model to work with. So, but I will let you know that I will convince you that this model has lots of applications, improve the performance of both machine learning and optimization service, and there might be a way to actually solve it to a satisfying performance. So to make things concrete, and on the left, I have essentially two sets of points. And they're generated by two different models. If you use one line to fit it in linear regression, it's a poor fit. If you use two lines, it's going to be a much better fit. So in this case, two experts or two models will do a much better job than one. So moving from a traditional supervised learning to unsupervised learning, we're looking at PCA, or principal component analysis, which try to fit a subspace to a set of points, where you essentially look for the normal direction of that subspace. If your points are constructed essentially generated by different models and use one subspace, you're going to be a poor fit. Here you can use multiple subspaces to fit it much better. And this model was roughly introduced in 2005 and have been cited thousands of times and have found applications in medical imaging. Okay, and so the power of sum of minimum does not just stop at the traditional machine learning models. It also allows us to do much better in large language models. So today, when people train large language model, it's not one model, it's actually multiple expert models, where when you type some kind of inputs, there's a gating function that sends the input to some of these models, and then there's going to be a scoring module that either combine or select the best answer. And this kind of moving from one gigantic model to multiple smaller models give you both better results and a faster inference time. To prove my point, I used the results from Mistral, which is a model that Mistral that came out of late 2023, and they compare it to Meta's Llama model. So here they have this Mistral 8 by 7 billion model, is 8 expert models of 7 billion parameters each, whereas Llama 2 70 billion model is much bigger model, 10 times bigger than individual models. Nonetheless, on all an array of performance measurements, the Mistral model is much better. Now, breaking a big model into smaller models means that you might be able to run these models in your traditional laptops, and maybe in the short future, you can even run it on your phone without internet. So GPT-4, although it's is a commercial model, nobody knows exactly what it is, but according to interviews, GPT-4 is a combination of 16 expert models, where every model is only about 55 billion parameters. And those all 16 models together has over 1 trillion parameters. All right. Okay, so this mixture of expert approach, or like a this multiple expert approach, is just not limited to machine learning. It also applies to mixed integer programming. Yeah. How do you do the inference? Good question. Okay, so when you don't have a very simple performance measure at inference, you will have to introduce some kind of score function that picks the best model out of it. But in optimization, it turns out we can calculate the optimality measure. We can measure time, so it becomes obvious. All right, so here I'm presenting you a highly simplified diagram of a mixed integer linear programming solver. And the actual solvers on a commercial level. Commercial level is at least 100 times more complex than this, because mixed integer programs are essentially lots of clusters of very different structured problems. And every component in the solver is designed essentially for one type of structure at one stage. And to have a solver that works out of box, people have to make lots of decisions. For example, whether to take a pre-solving procedure, use it or not, because you might waste time running the procedure and only get worse performance. And also in lots of the internal modules, there are going to be iterations where you have to have thresholds. So I claim that top solvers like Gurubi use highly optimized problem-aware configurations. So that configuration, or the heuristics that decide when you have a problem which configuration to use, is actually more complicated than individual components. Now, to prove my claim, last year we uploaded this report, which is an adapter for Cplex. So Cplex, we took Cplex and then produced an adapter which decides the configuration for every given problem. And then on the public benchmark set, this result surpasses Gurubi in all tests. So here is what we got. Give you a little bit background. MIPLib 2017 is a set of real problems, very different from small to large, with 240 real problems that assembled by Zib. And then there are additional 45 pathological problems and additional 32 infeasible MIP problems. And they are very challenging because till this day, no solver can solve all 240 problems in 7,200 seconds. That's about 2 hours. So this is Cplex default. This is our adapted Cplex, which is essentially some kind of a configuration optimization. Make it, instead of one solver, we make 100 solvers. So we are able to not only significantly reduce the average time, we also be able to solve more toward the 240 goal. To put it in context, this middleman's benchmark, we used identical machines, in other words, CPUs and memory as middlemans, and we put our adapter for Cplex, and we were able to surpass Groovy. Okay? And when we moved to pathological problems, we were able to solve all the 45 pathological problems also in shorter time. And when it comes to feasibility testing, we're able to detect 31 out of 32 infeasible problems using less time again and doing better than Groovy. So Groovy compared to Cplex, probably initially designed by the same set of people. So Groovy compared to Cplex, I believe, they did two things. Number one, make the solver engineering ground up for multi-core processors. Number two, they have much better configuration determination at runtime. Okay, so this, hopefully, I convince you that the power of using multiple experts solving one problem at the same time. So I think if you have a cluster, the best way to solve mixed integer linear program is not to try to parallelize the internal algorithms. Instead, just to come up with different configurations that are somehow orthogonal one another so that they can specialize to different sets of problems and then send a problem to all the solvers simultaneously. See which one gets the solution fastest. And this is because default configuration is usually very conservative and it's chosen such that the solver is robust, not necessarily fast, adaptive to the problem structure at hand. And about 10 years ago, Ted Rolfs of Lehigh, he and his colleagues organized some efforts, great efforts, to parallelize mixed integer linear programming solvers. And they basically discovered when you scale it up to over, let's say, about 20 threads, the average performance comes down, it's not increased. That's because the branch bound tree of most MILP problems are highly imbalanced. It's become very difficult to parallelize. Okay, now, so in summary, I think the key, the magic of the mixed experts comes onto solving this kind of problem, where we find the optimal assignment of each data point Fi to the model that performs best on that. And this is the unsupervised learning part because this minimum is decided without labels. And we simultaneously optimize all the K models. And this optimization can correspond to either supervised or unsupervised learning, depending on how you write down the loss function Fi. So this concept is related to multitask learning, ensemble learning, model agnostic meta-learning, but there are important differences. In all these previous paradigms, the clustering part, if there is a clustering part, it is supervised. Okay. So, as I mentioned, I've been mentioning the word clustering a few times. We can reformulate the sum of minimum model equivalently into this clustering minimization model, where the external or the major decisions are decided on disjoint partitions of the data points. We have to assign each data point to a cluster. And once it's assigned, internal minimization simply minimize the model over the data sets that are assigned to that cluster. Now, when I write the problem equivalent in this form, you can see that this generalizes many clustering models. For example, the K-means model, where every Fi, the loss function is simply the distance to a given point. So how do we solve the model? We take two stages. The first stage is a very careful, skillful initialization of the points of the initial models. This is inspired by K-means method back from 2007. And then it's a very simple procedure, like traditional EM algorithm, which we just greedily assign every point to the best performing model so far. And then with the Simon fixed, we apply either stochastic or standard gradient descent to update the individual models. And we repeat this process. So a lot of work is actually put onto this careful initialization part. So this initialization essentially choose a set of functions and use their individual minimizers as initial points. How to choose that set of functions? So we uniformly sample one function out of the n data points. Let me repeat, correct it. We uniformly sample a data point from n data points, and then find the model that best fit that single data point. We call it x1. Now we have the initialization of the first model. Then to resample, to get the second model, we have to look at the model performance. So we use the current model fixed and then measure the performance in this way. That is the take any other data point minus the best possible performance on that single data point and see the performance gap. And we normalize, we weight the sampling using these weights. And that allows us to sample a function that performed a data point where the current model performed rather poorly. After we sample the second data point, we use it alone to get the second model. And then we look at the functions that perform poorly on either of the existing models, and then use that weight to sample from the remaining function. And that'll give us the third model. And we do this iteratively until we have k models. We call those the initial models. So how does this perform? By the way, if you have trouble calculating a loss function, you can use the gradient.
Model is more likely to be selected.
So in other words, from an n data points, we select k, which k is usually much less than n. Essentially a set of only k data points, and they are spread out and may have a good chance of representing different clusters. And we use their independent minimizers as the starting point. This strategy appears to work really well. We simulated data in different dimensions and simulated true number of clusters, 4, 5, 6. And then we compared different initialization methods on this mixed linear regression model. Random means that you Gaussian randomly generate those xk's. Uniform seeding, that you just don't do the weighting. This is the proposed model that weights according to performance. The first letter is the misclustering rate over 1,000 rounds. The second one is number of iterations. So using this initialization and coupled with the EM method, you get both better misclustering rate and fewer number of iterations needed to converge. And the same is observed on training small neural networks. And here we use multiple neural networks. And we only tested on 2-layer neural networks so far. And this is the training, this is the loss function. Psi represents neural network, and theta j represent neural network parameters. And then we synthesize the set of points using the true model. And then we add some strongly convex regularizer to make the process more stable. And then we compared to different initialization, and it turns out the initialization performed the most important role so far. And then we came back and looked at generalized PCA. When people do generalized PCA, one of the most recent methods that also happen to most similar to our method is this smooth approach. let me explain what's going on here. So the decision variables are A1 through AK. They are matrices. They represent the normal directions of those subspaces. And then these, by the way, these subspaces don't have to be orthogonal one another. They just need to fit the data. But you just don't tell them which data they should fit. They should figure out which data they fit by themselves. So this model, this generalized principal component analysis can be modeled in using our sum of minimum model this way. This measure is smaller when a data point yi is closer to the subspace represented by its normal directions, aj. Now, when people solve this problem, they found this model very difficult to solve. So Penn and Vidal from University of Pennsylvania, they came up with the smooth model. And then so they can do a block coordinate descent on the smooth model. And then using their data, we compared our algorithms, and turns out the sum of minimum has much better success rate of assigning every data point to the correct subspace than them, and it's significantly better. So I'm almost running out of time now, just to give you the theory we have so far. Though obviously this is a very difficult model to solve, so we made strong assumptions, assume every Fi is L smooth and mu strongly convex. And then assume they altogether, we look at their minimizers, and assume at least there are k distinct minimizers. This is a standard assumption. And then we compare compared to some measures. This capital F star is the true minimizer of the sum of minimum model, true minimal value of the sum of minimum model. And this F star, little f star, is the ideal minimum because you individually minimize the performance for every data point. And the results we have is, if you initialize the points according to our procedure, then compared to the ideal minimizer, in expectation, the gap is less than or equal to this gap between the difference between them multiplied by log k and the condition number squared. So if we are doing a k-means, then the condition number is 1, and you get a constant 2 out of these big brackets. And in that case, we actually recover the best known results for k-means. And we also constructed the example. Initially, we look at this, this might not be optimal. And our student constructed an example which basically shows that this log k and condition number squared is necessary in the worst case. Not being proved unless you assume more structures on those f. And this is what we have on initialization. And there's not really much significant results we get on oscillating update. We get standard results. Essentially, it says from the initial point to the true optimum, this is the initial gap, there's like 1/t convergence on the gradients. And this is the gradient weighted by the cluster size at the time, and this is some kind of algorithmic results. Now, assume that those clusters are well balanced. They have similar sizes. Then you can go from this result and further show that for every class, for every model, you end up getting, you have, I'm missing a t here. You have 1/t convergence. Yeah, so I stop here, and to summarize, we believe sum of minimum optimization really represents a important and potentially powerful next step for machine learning paradigm. And there are a lot of things to really undiscover. I believe there are a better improved initialization because at the moment we only use function values or gradient to do the reweighting. It might not be optimal. Although we have numerically tested stochastic gradient descent and still get good results, our convergence analysis have not extended yet to the stochastic gradient descent regime. And then we need to derive more theoretical understanding, especially when the optimization part using stochastic gradient descent. And also, I'm not so sure if the greedy assignment to the clusters is optimal. Maybe non-greedy or somewhat stochastic greedy assignment can be better. We need to tackle large-scale application and data sets, especially training maybe small-scale or fine-tuning small-scale large language models. And I think the trend of large language model is moving toward this direction using mix of experts. So I think there are countless real-world impact. Yes, with this, I'll stop and open for questions.